hello. This is Gopal. Welcome back to physicsrankguru. Today we are going to discuss moment of inertia for continuous bodies. Today we are going to discuss moment of inertia for continuous body. Suppose you can consider the one rigid body. So this is the axis of rotation. I will consider this small portion of body dm. So this is from axis of rotation to r distance is there, r distance. So what is the momentum of inertia for continuous bodies? So di is equal to dm r square. Suppose I will get a whole body, so I integration di is equal to integration dm r square. Momentum of inertia for continuous bodies. So moment of inertia for continuous bodies. So di is equal to, suppose I will consider this is the axis of rotation, I will consider rigid body. So this is the dm. So this portion here to from rigid body to distance, perpendicular distance is r. So di is equal to m dm square. So here total, I will get total momentum of inertia. I is equal to integration di. So integration dm r square. So you will get total continuous bodies. So here note first one, for linear mass density, is equal to mass by length. For 1D, so this is described, linear mass density describes 1D. So lambda, linear mass density lambda m by L. So this is for a rod. So 1D, this rod is a one-dimensional body. So 1D, lambda is equal to m by L. So linear mass density lambda is equal to m by L. So second one, density, surface mass density, So we can write mass by area. So surface mass density, for we can use this one for two-dimensional bodies. So surface mass density we can write sigma is equal to m by area. So this is for two-dimensional. So this is for disc, etc. So next third one, volume mass density, you can represent mass by volume. So this is three-dimensional volume mass density, three-dimensional bodies. So here density is equal to mass by volume. So this is cylinder, etc. So linear mass density, mass by length. So this is for one-dimensional bodies. So lambda is equal to m by L for a rod, example rod. So surface mass density, mass by area. This is two-dimensional bodies. So sigma is equal to m by A per plate dot disc. Volume mass density, mass by volume. So this is three-dimensional bodies. So density is equal to mass by volume. for sphere, cylinder, etc. So an example, so find MOI of uniform rod of a mass m and length is L along the axis passing through one end of the rod. Suppose I will consider one uniform rod of a length is L, this length is L and mass is m. So I will consider this axis is one end, passes through the one end. So this is the axis of rotation. So for you can find out this, you can consider small element dm. Small element dm. The thickness is dx. So that is from axis to x distance is there. You can consider x distance. So here you can write. So what is the continuous bodies formula? So di is equal to dm x square. So this is the x, perpendicular distance is x. So di is equal to integration dm x square. So here I is equal to integration di integration dm x square. So here linear mass density lambda is equal to capital M by L. For small element lambda is equal to dm by dx. dm by dx. I want dm, so here dm is equal to lambda dx. But we know lambda is equal to m by L, so you can write dm is equal to capital M by L dx. So in place of m, you can write m by L dx. So integration, in place of m, you can write m by L. So here, so I m by L. So integration x cube, integration x square dx, x cube by 3 limits plus L2 by 2 minus L2 by 2. So here momentum of inertia I is equal to m by L. So here 3 is common, 3L. Here L cube by 2 whole to the power of 3 minus L by 2 whole to the power of 3. So here I is equal to m by 3L. So L cube by 8 minus or minus plus L cube by 8. So here I is equal to m by 3L. So this is 2 times there. So 2L cube by 8, 2 1 ja 2 4 ja. So 1L cancel, here square. So I is equal to m L square by 3 4 ja 12. So this is the moment of inertia for uniform rod about an axis passing through its midpoint. I is equal to ml square by 12. Third one, find moment of inertia of a uniform rod of a mass m and length is L about an axis passing through midpoint inclined at an angle. So this is axis. So here length of the rod is makes an angle some theta. So this is axis of rotation. So you can consider small element dm. So this thickness is dx. This is about from axis to x distance. So this is incline. This is theta. So this rod is moving like that. So this is from perpendicular distance you can find out this. So I will consider this is the r distance, r. So here I will consider this lambda linear density, linear mass density, total m by L for a small element, that is dm by dx. I want dm is equal to lambda dx. So here integration small element, so di is equal to dm x square. I want integration dm x square dm x square. So perpendicular distance, no, so here dm r square, not x square, dm, so dm r square, so here dm r square. You can find out this dm. So this is the length along the incline, so this is L cos theta. So here r is equal to x sin theta. This is what x cos theta. So other than theta is x sin theta, x sin theta. So here r is equal to, so integration dm is equal to, you can substitute lambda dx, integration lambda dx, r value you can write x sin, so x sin theta whole square. So here lambda is constant, lambda integration x square sin square theta dx. So here lambda is equal to m by L. Here sin square theta is constant, so you can common sin square theta, integration x square dx. So here m by L sin square theta, this is minus L by 2 from axis to, this is minus L by 2 and this is plus L by 2, plus L by 2. So here limits plus minus L by 2 to plus L by 2. So here x square x cube by 3 integration from, so here minus L by 2 to plus L by 2. So here I is equal to m by L sin square theta, So here L cube, L by 3 is common, so m by 3 L cube by 8 minus of minus plus L cube by 8. So here I is equal to m by 3L sin square theta integration, here 2L cube by 8, 2 1 ja 2 4 ja, 1L cancel, so here L square, I is equal to m, so 3 4 ja 12, m L square sin square theta by 12. So this is about moment of inertia about an axis passing through midpoint inclined at an angle theta. So I is equal to ml square sin square theta by 12. So next you can find MOI of a ring of a mass m and radius is r about an axis which is passing through its center and perpendicular to its plane. Suppose you can consider the ring, so that axis passes through perpendicular to its plane, so this is the axis, this axis passes through center and perpendicular to its plane, this is the axis of rotation. So you can consider a small element, that is dm, from center to r distance is there, radius of the ring is r. So here consider a small element. So what is the momentum of inertia for continuous bodies? Di is equal to dm r square. So here r is equal to capital R. So for whole you will get I is equal to integration dm r square. So from about 0 to m r square is constant r square integration 0 to m dm. Integration 0 to m is capital M. So here integration 0 to m dm is capital M. So capital M r square. So here therefore integration 0 to m dm is equal to capital M. So the whole mass. So I is equal to mr square. This is the moment of inertia about an axis which is passing through its center and perpendicular to its plane. I is equal to mr square. So next you can find MOI of disk, mass of m and radius is r about an axis which is passing through its center and perpendicular to its plane. Suppose you can consider a disk, this is the disk, the axis passes through its center, perpendicular to the plane. So you can consider a small element. So this radius is r, the radius of the disk is r. You can consider a small element of a ring, small element of a ring. The thickness is dr. This thickness is dr, and the distance from the axis is r. So this is a disk is a two dimension, that's why. So surface mass density sigma is equal to capital M by A, m by mass by area. So here area is m by pi r square. Area is pi r square. For a small element, moment of inertia di, di is equal to dm r square. For whole moment of inertia I is equal to integration dm r square. Consider this element, so straight it. So this is the elemental area. So this thickness is dr, and this is circumference of a circle is 2 pi r. This is 2 pi r. The length is 2 pi r. So here dA, area of this element, dA is equal to 2 pi r dr. Small element, this pi is equal to dm by this area 2 pi r dA, dm by dA is equal to dm by 2 pi r dr. I want m dm, so dm is equal to pi 2 pi r dr. So substitute this dm value here. So integration pi 2 pi r dr r square, So here pi is constant, 2 pi also constant. So here r square integration r cube dr. So you can consider the element. So 0 to total r, So this r2 limits r2 0 to r, you can consider 0 to r, from 0 to r. So pi value is m by pi r square, into 2 pi. This integration r cube dr is r to the power of 4 by 4 limits from 0 to r. 2m by r square. This is r to the power of 4 by 4. So here r square cancel means here 2. So here 2 1 ja, 2 2 ja. So integration I is equal to m r square by 2. M r square by 2. This is the moment of inertia about axis which is passes through its center and perpendicular to plane. Moment disk, this is about for disk. Moment of inertia, moment of disk of a mass m and radius is r about an axis which is passes through its center and perpendicular to its plane. I is equal to mr square by 2. So I will consider total. So this is a total disk of a mass is m and radius is r. So I will consider small elemental ring. So the thickness is dr. So from center to the distance is r distance. So this is two dimensional. For two dimensional surface mass density m by a m by pi r square. So I will consider this element. I will did state. So 2 pi r. So thickness is dr. So circumference of this ring is 2 pi r. So dA is equal to 2 pi r dr. So here pi for small element pi dm by dA. Dm by this area is 2 pi r dr. So here dm is equal to pi 2 pi r dr. So here substitute here in place of dm pi 2 pi r dr r square. So after simplification you will get I is equal to mr square by 2. So this is about disk of a mass m and radius is r. So sixth one, moment of inertia of a disk about an axis which is passing through its center and perpendicular to its plane. So here mass of the disk is m and radius is r1 and r2. So here two radiuses are considered. So this is a disk. So this inner radius is from axis to, this is the axis of rotation. So this inner radius is r1, this outer radius is r2. So here you will get same, this is the disk, small element you can consider, you will get. So similar process you can do. So I is equal to m r1 square plus r2 square. M r1 square plus r2 square by 2 will get. So I is equal to m r1 square plus r2 square by 2. So this is for mass m, ring of mass, disk of mass m, and radius is, inner radius is r1, outer radius is r2. So we will get moment of inertia m r1 plus r2 square by 2. So next one, so moment of inertia of a hollow cylinder of a mass m and radius is r about an axis of symmetry. So you can consider hollow cylinder of a mass m and radius is r. The axis is passes through exactly symmetry. About an axis of a symmetry. So this is, you can consider a small elemental ring element. So this is a ring. So consider a small elementary of a ring of mass dm. So this is what radius r. So I will consider, so here di is equal to dm r square. So here the radius small r is equal to, you can consider capital R. So here di is equal to dm r square. For you can do integration, you will get moment of inertia of cylinder about an axis. So integration 0 to m. So here r is constant, r square is constant, integration 0 to m dm. So integration 0 to m dm becomes what? Capital M. So here r square capital M. So here I is equal to m r square. So this is similar to ring. So moment of inertia of a ring mr square. Here hollow cylinder also mr square. So here this is ring. So here infinity number of rings. Hollow cylinder means you can consider small element, infinite number of rings you can consider. So here hollow cylinder is equal to infinity number of rings. Cylinder is equal to infinite number of rings. What about the ring momentum of inertia? Mr square. Hollow cylinder moment of inertia also mr square only. So this is hollow cylinder about an axis of a symmetry. I is equal to mr square. So here MOI of ring is equal to MOI of hollow cylinder is equal to mr square. So for ring and hollow cylinder, both moment of inertia is mr square. Moment of inertia of solid cylinder of a mass m radius r about an axis of a symmetry. So I will consider this is a small solid cylinder. So solid cylinder. This is axis of rotation. So I will consider a small elemental part. So this become as a disk, small element disk. So this is dm. For total here dm is equal, di is equal to dm r square. This radius is equal to what? R, radius r, dm r square. So di cylinder is equal to solid cylinder is equal to infinity number of disk. So here di is equal to dm by 2 r square. So you can find out momentum of inertia I is equal to, so here integration 0 to r, integration 0 to m, dm by 2 r square. Here r square is constant, r square by 2 is constant, r square by 2, integration 0 to m dm, become total mass. So here r square by 2 into m. So here you can write m r square by 2. So this is di, this is moment of inertia of solid cylinder of a mass m about an axis of a symmetry. I is equal to mr square by 2. So this is similar to disk. So MOI of disk is equal to MOI of solid cylinder. Solid cylinder is equal to mr square by 2. So both moment of inertia of a disk and a solid cylinder, both MOI same, so mr square by 2. So solid sphere, hollow sphere, so we can discuss tomorrow, and cone, hollow cone, we can discuss tomorrow. So all of you watch my videos and like, share my videos, and please subscribe
my channel, Physics Rank Guru. So all of you bye, take care, have a nice day.